Hello and welcome back to another VMK in the game development series. In this VMK, I'm going to introduce you to the Caligari file format. Up until now, we have been working with 3D objects by basically going into our code and programming the coordinates for all the vertices, all the texture coordinates, as well as all the colors that the object is supposed to take on. Well, whenever you're starting to create more complex games, creating geometry manually, the way we've been doing it up till now, is very tedious. And you don't want to do that. You want to take advantage of 3D modeling packages which can manipulate 3D objects in 3D space much more easily than you could by programming things manually in C code. So what I've done is I've gone through and took a look at what 3D modeling packages are available for free to everyone. And I was able to find that Caligari has a software package called GameSpace Lite. And it's targeted towards hobbyists who want to make computer games. That's what we're doing here. We're making a game engine that's going to use OpenGL as the renderer. So I'm going to take advantage of GameSpace Lite so that we can create 3D geometry using this 3D modeling package. And what this will do is we can then save Caligari's file format as a file, which we can then import into our game engine. All the sort of construction of the geometry as well as the textures and the materials, all of this will be automated, similar to how we did the parsing in the previous set of videos, where we had simple geometries for a cube, a cylinder, and a flat grid. Well, now what we're going to do is we're going to create another kind of geometry which will take into consideration what we're loading from this Caligari file format. But before we can get to that point, we need to understand how Caligari works and how the file format is saved. So what I've done is, under the download section, I started a new sort of section just for Caligari, which is located here. So in the next little while, you'll be seeing a bunch of VMKs showing up here, which are going to go over how to use Caligari software to do 3D modeling, as well as how to use it to paint on top of your models and also texture them. So you can handle all of the art pieces of your game using Caligari. Then, once you have all your Caligari files saved, you might have one file for, I don't know, a player character, you might have another file for a monster, you might have another file for vehicles, things like that. Once you have all these different files, what you can then do is load them into the game engine, and the game engine will automatically generate everything it needs so that it can render it on the screen. This is going to be a big time saver. It's going to open up doors to possibilities which you weren't able to do before. Let's start off with discussing the Caligari file format. If you go to the Caligari website, which is www.caligari.com, and do a search, you'll be able to find this document, Caligari two-space file format. Now, you're not required to go to their website and dig this document up, because I'll actually provide it to you inside of this VMK. You'll find a PDF inside there. So if you open this document up, you'll notice it's a little bit dated. It's July 2002. However, most of the material in here is still good. So if you scroll down through here, you'll notice there's an introduction and a description of how the file format is structured. Now, one thing to notice here, this document is 102 pages long. We're not going to go into the C++ code and create a parser that will parse all the different kinds of formats that this file can contain. Instead, we're just going to pick and choose the ones that we're going to be using, and everything else we're just going to skip. Now, the way that the Caligari file format works is the following. You have a header file at the very top of the file, and it identifies the file as being a Caligari format. It also has some information in there telling it what version number, as well as some other components in there. Using this header file, you can identify whether this is a file that you're going to be able to support or not. Once you do a decision at this point, you can then start parsing these things called chunk headers. And the chunk headers are sort of sections which pertain to one of these different kinds of chunk types. So you'll notice that Caligari basically saves absolutely everything it can so that when it loads a file up inside of its software, it knows how to reconstruct everything to how it was saved at the moment that you saved the file. So for instance, it saves anything to do with audio, which we're not going to care about. It saves where the camera was positioned. It saves how you've deformed objects. It has absolutely everything in here. And like I said before, we're not going to go in and create a parser to parse everything. We're only going to go through and actually choose 4 of these items that we're going to be parsing. And I'll show you the subset in a second here. There's also a brief history as to how the Caligari file format has been changed over the years. The first released version of Caligari software, I think, was 3.0. And it only had a subset of these different kinds of chunks available. Then as different versions of the software came out, extra chunks were modified, extra chunks were added, and all this history is shown under here in the history section. You don't really have to worry about this too much, but if you are using an older version of TrueSpace, you may need to take a look at this history to make sure that whatever we're programming will still be supported with older versions of TrueSpace, if that's what you choose to use. I wouldn't recommend it. I would say go and download GameSpace Lite or purchase GameSpace, even better, so then you have a full subset of everything that we're going to do in these videos. Alright, so let's go through and take a look at how this Caligari file format is structured. The format actually pertains to 2 different types of files. In TrueSpace, you can save things called Caligari objects, or you can save Caligari scenes. The only real difference between these 2 file types is that a Caligari object will contain one object in its file. A Caligari scene can contain a scene which contains multiple objects. For the most part, we're only going to be saving COB files because we want to separate our objects into separate files. Like for instance, if we created a scene that has a Jeep with some barrels and then like a house, for instance, you could save all of that information under a scene and then you'd only have one file. But you could also go ahead and, for instance, select just the Jeep, save that as a COB, select just the house, save that as a COB, and select the other items and save those individually. How you structure your game engine doesn't really matter so long as you know how you can pull data out into your game engine whenever you need to move it, animate it, or whatever. So be aware, there are 2 different file formats, file types, but both of them pertain to the same file format. They both contain the same structure that was outlined in this document. Now, how is this Caligari file format structured? Well, all the files are chunked files. Have a read through this introduction to get an idea of sort of a big overview as to how Caligari files work. There are 2 flavors of Caligari files as well. I mentioned here that you can have object files as well as scene files, but each of these can be saved as either an ASCII file or a binary file. And this is very important because we're going to be creating a parser that only reads in the binary file format structure. The ASCII file format is going to contain the exact same data that the binary file format contains. However, the binary file is actually going to be much, much smaller. A binary file is actually much easier to parse than an ASCII file, and you should already have experience parsing an ASCII file from the previous VMKs. So I've chosen to choose binary file because mainly the files are going to be smaller and it is easier to parse. Now, okay, so let's take a look here. The first item that we need to parse is this thing called Caligari header. And the header itself is going to be structured in the following format, in this order. So the first 9 bytes of data saved inside of a Caligari file should contain Caligari with a space after it. After that, you should find v00.01, and this just gives you a version number. Then there's going to be a code, a 1-byte code that's either going to be the capital letter A or the capital letter B. And this is going to identify whether this file is an ASCII encoded file or whether it's a binary file. And as I said before, our parser is only going to work with the binary file format. So we're going to be looking for this B to be present inside of the file. Then we have some other parameters in here which we're not really going to worry about, but we do need to read them in, because if we don't, then the parser will break down. So this is the structure for the Caligari header. It's the very first thing that we're going to read in. Then what we have is chunk headers. And a chunk header is going to be a section of code that basically looks like this. It's going to have 4 bytes that identify what chunk of data is going to follow this chunk header. It's going to have 2 bytes to tell you what the major version as well as what the minor version number of this specific chunk is. And this is important because different versions of Caligari's files will have different version numbers. So for instance, if you saved a 3D scene using TrueSpace 3.2, then that geometry may be saved using a certain chunk that's a version maybe 1.0. However, in a newer version of TrueSpace, that same chunk may have a different version number, which means that the structure of that chunk is going to be slightly different. And you'll see where this comes in a little bit later when I start talking about the specific chunks which we're going to be parsing. So this is the structure. Oh yes, this is also important. Each chunk has an ID number, similar to how when we did our previous VMK, we gave our geometries their own unique ID number, like GeoID. We gave textures texture ID numbers, and we gave materials material IDs. Well, all chunks have their own chunk ID number that identifies this is my own chunk. Each chunk also has a parent ID, and this is important because whenever you're creating a nested structure, this parent ID tells you which other chunk is this chunk related to. So you need to know this parent ID structure so that whenever we're loading in data for geometry, it will also have a separate chunk that says here's the material attached to it. Similar to how we did it in our own parser, but a little bit differently because the material is actually broken into a material chunk and a shader chunk. And I'll talk about this later as well. And finally, there's this last parameter here, that's the number of bytes in this data chunk. So each data chunk at the very top will have a header, gives you some information about it. Then there's a parameter that tells you how big the chunk is, so that if you do want to parse it, you can parse it appropriately. However, if you want to skip it, all you need to do is move this number of bytes forward in the file, and you'll completely skip the chunk, and you'll be starting at the beginning of the next chunk. So this is a very important field because you need this to know exactly how big each chunk is. There's some common elements within each of the chunks that we'll be parsing. Some of these elements are strings, and all strings are saved in the following manner. There's going to be 2 bytes which designate the length of the string, and then following this 2 bytes is going to be the actual string itself that's saved. And the string itself is just going to be plain ASCII characters. However, the string itself is not null terminated. This is important because in all of our C++ code, we depend on having null terminated strings. So what we're going to have to do is manually terminate anything that we read in from a string data type. Names inside of the Caligari file format are saved in the following manner. There's going to be a counter number, which is the first thing you'll find, and then following that is going to be a string. And the string is basically what I described here. It's going to be 2 bytes for the length of the string and then the string itself. So a name has this extra counter number. And the reason why it has this is because in Caligari software, anytime you create a new object, it gets named automatically. So for instance, if you create a cube, it's going to be called cube, and then it's going to be 0. If you create another cube, then it's going to be cube 1, and then cube 2, cube 3, and so on. So that number is associated inside of this parameter here. Certain chunks will have something called the local axis, and the local axis is going to be broken down into a bunch of parameters that identify the center as well as the coordinates for the x, the y, and the z-axis. We're not going to be using the local axis, however we will need to read it in so that we can skip over it appropriately. And again, this document outlines the ASCII file format as well as the binary file format. We're only going to be parsing the binary file format, so please only be looking down here in the table format. Don't worry too much about this part here. The current position is going to be a transformation matrix that tells you how to take the specific chunk that we're working with and position it in 3D space. It's actually a matrix that only has 3 rows and 4 columns. Normally a transformation matrix is 4 by 4. However, by default, Caligari does not save the last row, which is always 0001. So this is something we're going to have to reconstruct manually as we're parsing. And here's a structure for how that current position is saved inside the binary file format. And then down here is a gross listing of all of the chunk types. Now, to not overwhelm you with all the different kinds of chunk types, what I've done is I've taken this document and I've actually cropped it down to just the parts that we're going to be working with. Inside of the VMK's compressed file, you'll notice that there's this one PDF here which outlines the complete true space file format, but you'll also find there's this second document here which just describes a subset of the Caligari file format. So what I've done is I've just cut and pasted the introduction, the Caligari header, the Caligari information here on how the header is structured, how strings are structured, names should be in here as well, names, local axis, current position, all of that is in here. But then under the chunk types that we use in the OpenGL game engine, I've only listed the ones that we're going to be creating a parser for. So these are the only ones that you really have to understand completely. So let's take a look at these. The first one in the list here is the material chunk. And this chunk basically contains data in the following format. It has a chunk header. This is the same structure that I showed earlier. It has a material data, and then it has 3 optional fields: environmental map data, texture map data, and bump map data. These will be here if you use them. If you're not using them for the specific object that you're mapping this material onto, they won't appear. So you have to have sort of logic inside of the parser to identify when to parse these items and when to skip over them. Okay, so what does this material data chunk hold? Well, its binary file format looks like the following. It has a material number because every single object that you're going to be saving inside of the file format is going to be stored underneath this chunk called poly_h. And inside this poly_h chunk, there's going to be a structure for every single face inside of this object. And for every single face, you're going to have a material number. That material number is related back to this specific material number that you'll find inside of this chunk. So you have to make the connection between the material number inside of this chunk and the material number found inside this chunk. Then we have a shader type. You can either have a flat shader, a Phong shader, or a metal shader. We're not going to worry about flat or metal. We're only going to be interested in the Phong shader. Faceted types, you have the ability inside TrueSpace to select whether you're going to have a faceted faced object, an auto faced, or a smooth shaded object. We will support all of these, as well as whenever you select auto face, you get to choose your smoothing angle. So it can go between 0 and 180 degrees, or I guess it says here 179. So we're going to have to pull this number out and calculate the normals for our object appropriately so that everything gets smoothed properly. Material contains the red, green, blue, as well as the alpha channel for the specific color of this material. and it has some coefficients here. We're not going to worry about these values here because these values we're actually going to pull from a different chunk. And I'll talk about these in a second once we get to the shader chunk. Then we have the optional parameters here. We have the environmental map data, which is structured like so. And if you find this parameter here, E:, then you know that this data chunk exists. So you do have to parse it. If you don't find E:, then we can skip over it and search for the next guy, which is the texture data chunk. And if there is a texture applied to this specific material, then you can pull information on what is the file name of the texture that's being used, what is the U and V, which is the texture coordinates for the offset. The way we're going to handle these are with a texture transform. And then we also have the number of times to repeat this texture in the U and V direction. And we'll handle this with also a texture transform to apply a scaling to the texture so that we can increase or decrease the number of times that the texture appears. And finally, there's also a method here to save bump map data, but we're not going to handle this, so we do have to be aware that it could be inside the file, and if it is, we need to just skip over it. Alright, the next type of data chunk listed in here is the poly-H data chunk. And this is the polygonal data chunk which holds all of the vertex data, texture data, and face data. So this data chunk has a chunk header. All data chunks will have a chunk header to identify itself. It'll have a name because every object you can name. And this will be helpful because when we're parsing this, we're going to extract the name and apply this to the node transform so that when we need to move the object or rotate it, we can refer to its own name and then we'll be able to find it inside of the scene graph. It has the local axis, which we're not going to use, but it also has the current position, which is that transformation matrix. We are going to pull this and save it. It has local vertex listings, so this is a complete list of all the vertices that this object contains. It also has a UV vertex list, so this is all the texture coordinates that we're going to be needing. And then it has a face list, which basically is an index number for this one and an index number for this one, so that you can say, okay, this face is made up of these following coordinates and these following texture coordinates. And finally, there's some additional flags which we're not going to worry about, but we need to skip over them, so we will need to parse them. Alright, if you look through here, you'll see that the local vertex list is saved in the following way. First, there's going to be the number of vertices that are going to be contained, and then following that, there's going to be 12 bytes for each vertex that is contained. And 12 bytes because a floating point number is 4 bytes, and 3 floating point numbers are required to specify a vertex for X, Y, and Z coordinate. For the UV vertex list, which is the texture coordinates, you only have 8 bytes per UV index. So the first thing in the list here is going to be the number of UV vertices, and then for each one you're going to have the U and V coordinate, which is the same as the S and T inside OpenGL. And finally, the face list, what it contains is 4 bytes for telling us how many faces or holes this object has. Now, the difference between a face and a hole is a face is actually a piece of geometry that makes up a triangle. A hole is a piece of geometry where the triangle does not exist. So what we're going to do is we're going to look through and only save the faces, because the holes we don't care about. We're not going to render holes because holes are holes, so we don't want to see them. But faces, we do need to see them, so we're going to save all the faces to a data structure so then we can go and render them. The other thing I should have mentioned earlier, but I forgot to, is that inside Caligari software you can make non-planar faces. This is a bad thing inside OpenGL because OpenGL does not really render nicely non-planar faces. So to avoid this, what I'm going to impose is a restriction on the number of vertices per face, and that's going to be 3. So any time that you create any object, you're going to have to triangulate it. And that's not a problem because Caligari actually has a nice button to triangulate all your objects. So all you do is select an object, hit the button, and then bam, all of a sudden your object is now triangulated and you're ready to go. So we're going to be using that quite a bit. Alright, so here's the structure for how faces are saved. There's going to be a flag that tells you whether this is a hole or whether this is a face. And the flag here is going to be this bit here, which is bit number 3. So if bit number 3 is set, it says here F hole flag is not set, which means it's a face, and F hole flag is set, which means that it's a hole. So we're going to be looking at bit number 3 to identify which of these it is, so that we know whether we're working with a face or whether we're working with a hole. We're only going to be saving faces, so down here we're going to look for the number of vertices per face, and we're going to make sure that this is always equal to 3. As soon as we find one that's not equal to 3, we're going to generate an error message. For each face, we have a material number, and this is that same number that I was referring to earlier when we were talking about the material chunk. So each face is going to say, okay, I'm material number 0. You're going to have to go through the material chunk to find material number 0, so then you can figure out what color and other parameters are there for this specific face. Finally, for every single vertex in this face, there's going to be a pair of indices. There's going to be an index for the vertex, and there's going to be an index for the UV vertex. So using these two indices, you'll be able to pull data out of either, where is it here? Either this structure for the XYZ coordinate or this structure here for the UV coordinates. You'll see how this works in the next video tutorial once we actually start programming. This video, I'm just going to go over how the structure works. And then down here, let's see, is there any other information? We have, this poly H data chunk is dependent on the current version number. So if the minor version number is greater than 4, you will have this extra parameter, which we have to read in, or else the parser will be pointing at the wrong spot inside of the file. So if we have a version number greater than 4, we have to look at this, but we're not going to actually use this parameter for anything. Same thing is if the minor version number is greater than 5 and it's less than 8, then we're also going to find this other parameter here, which we're not going to use, but we do need to read it in. Alright, next chunk here is the shader chunk, and this is the chunk that contains additional information that we need for the material node that we can construct. So inside here we're going to have a chunk header, we're going to have a color shader data, transparency shader data, reflectance shader data, and displacement shader data. Now, you'll notice that the information inside of this SHBX chunk is slightly different from the information that is found inside of the big Caligari file that has all of the data chunks. When I was constructing the parser for the Caligari software, I noticed that the data format for the Caligari software inside of that big file, the 102-page file, did not actually match with what I was getting when I was saving files. So I contacted the people at Caligari software and said, okay, listen, there's something wrong with the shader chunk here. Can you explain what's going on? So they gave me, they fired back an email to me, and they told me specifically where I was going wrong and where the bug was inside of the document. So what I've done here is I've actually rewritten this document in this version here to match the correct output from GameSpace Lite as well as from TrueSpace version 6.6. So make sure you look at this one and not the other document, the 102-page document. Okay, so first thing we're going to read in is 1 byte of data. It's going to tell us which of the 4 kinds of data we're going to be pulling from. Next thing is going to be a shader identifier, which is a string, and all strings are going to be size 2 plus the length in bytes of the string itself. And then it's going to be followed by a number, which tells us how many different kinds of parameters there are down below. You'll notice that inside of the 102-page document, it says that this should be, I think, a char, which is a 1 byte. However, the data that's stored inside of the Caligari software is actually 4 bytes. So this is one of the distinct differences between my document and the other Caligari document. Now, for every single parameter that we have here, we're going to have the following structure. We're going to have a string which identifies the parameter that we're reading, and then we're going to have a number that tells us what kind of data type this parameter refers to. So we could be reading in integers, floats, vectors, colors, anything basically in this list. And then depending on these numbers, we're going to have one of the following data types that we need to read in. So for instance, if this data type here says it's going to be a color, then this number here is going to be 7. And then because it's 7, we go down to the here, and to extract all the parameter values, we'd say, okay, we got 7 before. That means we're going to be reading in red, green, blue color values, which range from 0 to 1. So we're going to be reading in 3 floating point numbers to get the red, green, and blue values. After reading in all the parameters here, there's one other parameter which is called a flag, and it's a short value, so it contains 2 bytes. I think the default is 3, and this parameter here is also not mentioned in the 102-page document. So be sure to include this in the parser, or else you won't have your parser working at all, as I found earlier. Alright, and then finally we have the end chunk. And the end chunk is basically the terminator that says there is no other data after we read in this end chunk. Similar to how we had the end keyword inside of our own parser file, Caligari has its own end here that indicates there is no more data to read after that. So those are the 4 data chunks we're going to be parsing. We have end, we have the shader chunk, we have the polygon data chunk, and then we also have the material data chunk here. Okay, so make sure you read through this document, print it out, make any notes that you don't understand. Feel free to email them to me or post them on the news groups, and I'll help you understand what this data actually means. Now, to get a better understanding, what I would highly recommend is fire up TrueSpace or GameSpace, whichever you're using, and create a very simple geometry. What I've done here is I just created a box, and I've painted the sides here to be, well, let's see, I have red, I have green, blue, yellow, and then I also textured the very top of it. I positioned the box in such a way that it's 0, 0, 1, and I rotated it to be 30 degrees rotated about the z-axis like so. I also triangulated it. You'll notice that there's a button here, Triangulate Object. If you hit that, then the object becomes triangulated, and you see that each face is broken up into 2 triangles. Once you've done this, then you can go under File, hit Save As, and you have the option here to save either as a scene or as an object. Remember, I was telling you, if you save as a scene, you can save multiple objects in one file. If you save as an object, you're only going to save the currently selected object to your file. So hit Object, and then you can save as a Caligari object, or highlight as a COB file here, and you can save it as a binary file, which is the default, or you can hit the checkbox here and save it as an ASCII text file. So what I've done here is, for this specific box, I've saved both a binary file and an ASCII file. So now, once you've done that, go into your directory, wherever you saved your files here, and open these up and have a look through them. So here we go. We have our Caligari text file. So this is the ASCII file version of that box. You see, here's the header structure. We have a Caligari file format, and it's ASCII because there's a letter A right there. It has some header information here for the data chunk called bitm. So if you want to understand what bitm is, you can go into that giant document, the 102-page document, and read about what bitm is. Then if you scroll down here, you'll see, okay, here's polyh. This is the one that we're going to be parsing. So polyh, the current ID number for this chunk is the following number, and there is no parent, which means it's basically at the root. The size of this data chunk here is 1,144 bytes long. All right, interesting. The item itself was named cube, so here's the name itself, and then we have the following information, which we're not going to use. And then we have our transformation matrix, which we are going to use. We are going to pull this data and save it for our own uses. And then take a look here. We have all the vertices. We have vertex number 1, so we have -1, -1, -1. Vertex number 2, -1, -1, and 1. Actually, sorry. Everything is going to be index 0 inside of our code. So this right here is going to be vertex 0, vertex 1, vertex 2, and so on. Then we have our texture coordinates. We have 0, 1, 0, 0, 1, 1, 1, 0, and so on. So everything is textured for us. So all the faces which will have textures could be using these vertices here. And then finally we have 12 faces for our cube. Our cube has 6 sides. However, because we've triangulated, each side is broken up into 2 triangles. So that's why we have 12 faces. And we can see here, okay, we have face with 3 vertices, has flags of 0, which means this is actually a face, not a hole. And it's going to use material number 4. So we haven't hit the material chunk yet, but once we do, when we find material number 4, then that means that this face is going to use material number 4. And this face is made up of vertex number 3, vertex number 2, and vertex number 0. So if we go back up here, we can see, okay, vertex number 3 would be 0, 1, 2, 3. So it's this coordinate, and then vertex 0 is this coordinate here. So those 3 vertices make up our triangle. Then our texture coordinates for that triangle is 3, 3, and 1. So if we go back down to here, we have 0, 1, 2, 3. So we're going to have this one twice, and then we have this one here. So that's the structure of how to read in these faces. Then we have some drawing flags. Then we have another chunk data here called unit. We're not going to worry about that. We're not going to worry about this one here. We're not going to worry about this one here. You'll notice there's actually a lot of data stored inside of this file. Okay, here's our material chunk, which we are going to worry about. You'll notice it has an ID number, and now there's a parent. And if you look closely, the parent number here actually refers to the ID number for this poly chunk. Both of these match because this material is associated with that polygon. So that's why we have these material numbers that we have to reference to one another. Inside of this material chunk, we have material number 0. It's a fawn that has been auto-shaded with 32 as the angle for the normals. It's made up of a face that's colored white because its red, green, and blue values are 1, 1, 1. Alpha value is set to 1, and then there's some other parameters here which we're not going to use. Here's a shader chunk, which has a parent equal to this material. So you notice that all shader chunks are parents of materials. This is also important because of the way that we're going to be parsing. Okay, then we have the first item here is the color. Well, the color itself is going to be a plain color, which is going to contain one parameter, and the parameter is going to be called color. And the color of the color parameter is 255, 255, 255, which is white. This one should match up with the original white that we had saved right here. You'll notice that this value will always be this value here if they're the correct parent-child relationship. Next thing is the transparency. Here we have shader none, so we have no parameters, so we don't have any transparency attached to the specific material. The reflectance for the fawn, we have 5 parameters. We have an ambient factor, diffuse factor, specular factor, an exponent, and then specular color. We are going to be using these values to figure out our ambient color, our emissive color, our diffuse color, and our specular color. Specular color is obvious because it gives it to us right here. But ambient, diffuse, and emissive, we're going to have to infer from the data that's saved in here in this data chunk. Finally, we have displacement, which we're going to skip over, so we're not going to worry about it. So basically, go through. Here's another material chunk you can take a look at. Yeah, this one is with the texture. You notice that we have a texture map associated with it, and the texture file is called Caligari.tga. That was that Caligari texture that was on top of the cube. It has some S and T values, which are U and V basically, repeat values here as well. So go through and try to reconstruct in your head what all this information is. Because what we're going to be doing is, in the parser, we're going to be taking all this information and putting it into C++ so then we can use it inside OpenGL. Once you're comfortable with how the information is stored inside of the text file, then start looking at the binary file. Now you'll notice that in the binary file, you can read the first line of text, but that's basically it. I mean, it tells you it's a binary file because there's a B right here, but then everything else is in binary, so you can't read it inside of a text editor. What you're going to have to do is install a hex editor or a binary editor so that you can read the text. What I recommend is going to go to this website, www.hhdsoftware.com. And on here they actually have a hex editor software package. If you click on hex editor, you'll notice down here there's a free hex editor. You can just hit the download button and you'll download the hex editor, and it basically looks like this. If you load up that cube_bin cob file, then you'll now be able to look at the binary data that's stored inside of this file. And this is, I can't tell you how invaluable this is. This is basically how I was able to identify that there was bugs inside of the Caligari file format rather than bugs in my code. I could see specifically that the data that was being stored inside of these files did not match the file spec. So once you create a simple cube and you start looking through the binary file format, make sure that you understand how the binary data is saved in here and compare it with the ASCII file data that's saved in here. Basically everything you see in here is the exact duplicate in here, but just in binary. And if you look really closely, let's see if I can find some instances here. Okay, here we go. We have a poly H chunk. So right here, this set of data tells me that this is a poly H chunk. From there on, you should be able to step through by looking at this data chunk here. Let me just see where's the here. Okay, here's poly chunk. Just by stepping through, you'll be able to say, okay, the 4 bytes that refer to the local axis vertices, well, they should be wherever there should be inside of this file. You should be able to step through this and be able to pick off the exact numbers that you need for everything. And the numbers that you're pulling out of here should match up with the numbers that you find in the ASCII file. If they don't, then you know you're doing something wrong, and go through and look at the data in more precise manner. That's what I would recommend. We are going to be going through the parser inside of the next video, and I don't know how much I'm going to be going back and forth between the hex editor and C++. I don't think I'll be doing it very much, but it is very handy to understand how data is stored inside binary file format as opposed to a text file format. Alright, so I think that's it. That's all I wanted to describe in this video. Have a read through this document, print it out, keep it by your side so that when we start the next video, you'll have a clean slate and have a good start for what we're planning on doing and how to move forward.